this is the fourth or fifth video tutorial on automated gear train, reverted gear train design given target gear ratios. So in the past couple videos we have created this script here, which basically creates a model, creates our variables, defines objective function, and we make all of these constraints, and we have 26 constraints now. So the next step is to put these constraints into the model. So similarly to how we define the model variables, to create the model constraints similarly like this. Okay, so model.c1, constraint 1 is going to be constraint, and we set the rule for this constraint is equal to con fun 1, right? So the rule is the function that we're going to use. So we look at con fun 1. What the model is going to do, or what the solver is going to do, is it's going to put in n1 and d1 and p1, and this expression is going to evaluate to true or false. It evaluates to true, and then we're good on that constraint. If it evaluates to false, then we know something's wrong, and the solver will attempt to correct that. So this is what we're going to do. We're going to just type this out for every single constraint. You guys are. I'm going to go ahead and go over here to the completed one that I have. Okay, here we go. So now all of our constraints are in. Got to make sure they're all numbered right and stuff. So that should be fun. And let's just, in the interest of readability, again, put this comment. Create constraints for the model, and then we're going to create objective function for the model. Okay, so we do model.obj objective. So this is similar. Rule objective function, and then we do sense is equal to 1. Okay, so sense 1 means minimize. So that means we're trying to minimize the subjective function, which makes sense. We're trying to minimize the error. If you wanted to create a model where you needed to maximize, you would put a -1 for maximize. But since we're minimizing, sense is negative, or sense is 1. And so now we are going to solve the problem, finally. Let's do it. So for solving the problem, we're going to use that OPT thing that we imported earlier, the solver factory. Okay, and Couenne is our solver, right? Because that's what we want to use. So for this to work, Couenne needs to be the name of the executable file in your path environment variable. So your path environment variable, you know, depending on what thing you're in, but if we go to, like, I think mine is in US local, I think it's in the bin, so if we go ahead and do this, it should work, right? So that now we're in the Couenne. We know that Couenne is working. It's in my USR local /bin folder. So you need to make sure that wherever yours is, it needs to be accessible by it needs to be in your path environment variable. Otherwise, it's not going to work. So now we're going to go ahead and create an instance. Instance model.create instance. Boom. Okay. And then we're going to create something to hold our results. So we're going to do results as opt.solve, and we're solving the instance that we just created. And then we're going to do instance.solutions.store to, store to results. Okay, and print the results. Okay, so that's all, folks. We have created the PyMO model to solve for these two target ratios, solve for all the gear parameters, the center distance, what have you, everything, according to these constraints. Now, if you wanted to make a similar design, but not impose, for instance, if you wanted to go over here to the diametral pitch and just do positive reals instead, this will actually make an more accurate gearbox, but harder to manufacture. That's why we just did this, and I believe actually this upper bound is 80. But you can change this around to however you want. It's going to give you different results. For instance, for a design like this, we don't want to make it huge. Okay, this gearbox is about 14 inches in length this way, and about, I would say, about 20 inches this way. So we can, it's not that compact. So if you wanted to make a gearbox that's much more compact, you would change this bound for the diameter and make the diameter smaller, and possibly, if you want, bound the center distance so that we can get a smaller gearbox overall. So with all those considerations being said, let's go ahead and go down here, and we're just going to run it now. So I'm just going to close all of my open tabs that I have, and we're just going to run it, see if we get any errors, any things we need to fix. Looks like it's going good. So, oh, there's one thing that I forgot though. So we know this is running. It says cannot call model.create instance on a constructed model. Just basically means that we've already run it before, so the model's already created within PyMO, and we don't actually need to do this instant create every time. But just do it anyway. You don't have to, but I recommend strongly that you do that. So the next thing we want to do is, PyMO is super, it takes a long time. It's not like press the solve button and the solution's there like that. We're going to have to wait like 5 hours. So depending on how good you want the gearbox to be, you can wait like 5 minutes if you want, and you'll have a pretty good design. But for the PyMO to find a minimum for that objective function, it takes a very long time. And I've already run this problem for more than 24 hours, and it still doesn't converge on the minimum solution, because that's what it is attempting to do, is to find the absolute best combination of variables for our constraints and objective function. So if you don't want to wait for 48 hours for a good solution, what you're going to do is we're going to open up your text editor, and we're just going to put this in here: time limit, space, and then in seconds how long you want it to run. So for this, let's just, for the sake of time, we'll do half an hour. So that's 3600 divided by 2, which is what, 1800 seconds? Yeah. So we're going to save this file, and we're going to save it, and we want to save it to that same folder that we're working in. And we're going to name this coenne.opt. Okay, and this is the options that will get passed into the solver, so that it will only solve for a certain amount of time, and then will output the solution after half an hour. So as what we're going to do now is I'm going to run it, and I'm going to come back in 30 minutes at 10 o'clock, and we'll look at the results, and we'll calculate our error, and we'll see how good it is. So here we go. Alright, let's see. Okay, so now it's running. So in half an hour I'll come back. Alright guys, welcome back. As you guys can see here, the solver just finished solving the problem. It went a little bit over time, but it usually does. So these are the calculated values. We have an objective function. This is the value of the objective function here. And these are all of the parameters. We have the center distance, 17.75, which is pretty big, but whatever. We didn't really constrain this problem that hard. So now that we have all these values, and we have face width values here, we have the pitch values. So I have the spreadsheet set up here to take the standard pitch and the pitch circle diameter, calculate the number of teeth that we get, and calculate our error. So we're going to go ahead and put those in. So we can see here that we have a diametral pitch 4, 4, and 6. So we have 4, 4, 6, 6. Gear 5 has the same pitch as 1 and 2, so that's 4, and then 6, 6, 6 for 6, 7, and 8. Okay. Now we'll put in the diameters. So 8.75, 26.75. Oh, I made a mistake here. This is 4, 4 as well. Okay, so now if the math is correct, we should get all of these n values on this side, right? And it looks like we're good on that, and so we have a center distance of 17.75, which aligns there as well. And then we'll just take a look at the error that we get. As you can see here, we have 4.3 and 9.095, and these are very close to the target 4.3 and 9.1. As you can see, this is the percentage error, which is the difference between the target and the actual. What we have, the actual minus the target, the absolute value of that divided by the target, times 100. So that is the percentage. Oh. That's correct. E19. Yeah. Okay, so this is correct. E19. Yeah. Okay. So we have a total speed error of 0.06%, which is very good, but considering that we have a center distance of 17.75, this is really not very good, because if we want to make a gearbox, for instance, with 5 gear ratios, then we really want to keep it as compact as possible in terms of like weight and just material usage. As you can see here, we have some pretty thick gears, the thickest gear being 3.5 inches thick, which is pretty redonkulous. So we want to in the future optimization create this problem instance such that we can achieve smaller face width values and a smaller center distance. That way we have a smaller, more tightly arranged gearbox. Yeah, so that's pretty much it. That is how you can solve a mixed integer nonlinear programming problem with PyOMO and a Couenne mixed integer nonlinear programming solver. If you guys are interested in, the further design of the gearbox, which would entail, like I have another script here that I can run that calculates the stresses on the gear, the stresses on the gear teeth. It goes through and calculates those parameters that we kind of just estimated in our original run through of this problem. But in my actual setup, I follow a more exact procedure by which we calculate the stresses and the strengths of the gears. And then furthermore, we can design and find the needed shaft diameter to accommodate the loads the dynamic loads on the shaft. So that's what this script does here. We get the planar on the XY plane and the YZ plane moment on the shaft, and this is the counter shaft. So this is a bending moment diagrams. And then we calculate maximum moment, maximum torque, required shaft diameter, 0.69 inches for this design. So that means that for this design, we need on the counter shaft, we need a 0.69 inch thick shaft. So, I mean, if you guys are interested in how I did this, these programs here, those are pretty easy as long as you have an understanding of basic mechanics and physics. But other than that, this will conclude the series on how to design a reverted gear train with 2 target ratios in an automated fashion. I hope you guys enjoyed it, and I'll see you guys later.